It's my great pleasure to introduce today's speaker. Janok Bhattacharya is somebody who, in the course of a career, there are people for years and years who you may not have directly met, but you read each other's papers, you're aware of each other's work. I've long had deep respect and admiration for the work this gentleman has done, so it's really a pleasure for me to be able to welcome him here to Northwestern. And of course, whenever we have someone who comes to speak here who is a purveyor of sequence stratigraphy, it's kind of special to do it here in the Sloss room, because there's no one who does sequence stratigraphy who isn't aware of Larry Sloss and his legacy. Our speaker today hails from Canada. He did his undergraduate work in Newfoundland and then went on to McMaster to do his PhD work, and then spent years in the wilderness of Texas, working in and out of the oil business and academia, and ultimately returned to Canada, where he's a named chair at McMaster. I'm going to turn it over to you and take it away.
Thank you, Brad. So, so I was a PhD student at McMaster. Roger Walker was my PhD supervisor. Jerry Middleton was the scary guy on our committee. And the thing about Mac in those days is, Roger was he did his PhD with Harold Redding at Cambridge, and he was sort of the master of observational facies analysis of rocks, looking at rocks to understand, make good observations and accurate identifications of the key features that allow you to determine the deposition environments. But Jerry was the guy that he actually started off as a hexachoral paleontologist, but understood that there needs to be more physics in sedimentary geology. So he was adamant that, whatever you do in interpreting sedimentary rocks, you have to understand and honor the physics. Jerry died a couple of years ago, and so we had a special session at the CSBGU convention in Calgary, honoring his legacy. And I went back to an old project that I worked on that I'll talk about in this talk, looking at Permo-Triassic subsurface reservoirs in the Prudhoe Bay Field in Alaska, and since gotten this concept of source to sink analysis, trying to understand the origin of sediments, their transfer to the sinks, the budgets, and the physics that control those processes, all of which it requires good observations of the rocks and understanding the physics. I did get to meet Larry Sloss once in the early 90s when I was a postdoc in Edmonton. And Sloss had the same philosophy as a single-handed researcher as Roger and Jerry did separately. So obviously he's known for the famous Sloss sequences, but whether or not people understand the diagram on the right, where when I show this to students, I said, look, let's just make some ridiculously simple assumptions. The sediment comes in, it can't be stored in the basin, it goes out. What's the environment? Students scratch their head. Could be a desert, could be a river. I'm like, right, it's a pass-through deposition environment. What about the lower case where there's way too much accommodation and the basin can't be filled? What kind of deposition environment do you get? Deep water, you got it. And then we get to the middle where it's balanced, and that's the delta systems that I love to work on. But you notice that Sloss captures it in terms of some mathematics. Now, he never really solved the differential equations to describe these sedimentary phenomena, but he understood the importance of physics. And the last Sloss figure I'll show is this one, where he has a stratigraphic cross-section on the bottom. Admittedly, it's pretty simple, but he points out that you can either hold discharge constant and vary the subsidence, or you can vary the subsidence, keep the discharge, or vary the substance and keep the discharge constant, and you get exactly the same stratigraphic patterns. In other words, the observations of stratigraphy do not allow a unique interpretation. You've got to really work the problem from both and say, well, what's the evidence that the substance is changing versus sedimentation rate is changing? Can you detect that by thinking about it and observing it in the rock record? So it's key to integrate physical understanding with the observations. Okay, so I did spend some time in the wilderness, but my wilderness was more the oil business than academia. But having said that, when you work for big oil, there's lots of money, lots of data, and you get to solve some pretty cool problems. So I'll go through an introduction in which I'll sort of talk about some of the problems that we try to solve in the subsurface world. And if you don't like oil and you're a hydro person, groundwater, fluid flow in porous media, it's critical to understand the geology, regardless of whether you're servicing oil and gas or trying to clean up the messes or trying to get improved groundwater. And then I'll talk about little deconstructions from facies models, and then I'll go through a couple of examples. So here's a typical example. You've got some wells, you've got some channel belts, and you've got some oil in there. And of course, in this case, the wells hit the two gray channel belts and fail to capture the green one that's filled with oil. So the question is, what's in between the wells, right? And of course, fluid flow in porous media is controlled by the architecture of the barriers or the aquatards, and the aquifers or the reservoir seal pairs that we use slightly different terminology in the oil business. You may have thief zones, so super permeable zones that extract too much fluid. You know, and if you're pushing water into an oil reservoir to push the oil, and there's thief zones, and all you do is get the water, and the water flood doesn't work. So those are the kind of problems that we were trying to worry about in the oil business in supergiant fields, is how do you manage the fluids, water flooding, and secondary recoveries. And all of that requires a good knowledge of the geology. So these are the kind of diagrams that geologists like to draw. So we've got some cross sections of a brown river system feeding a yellow delta, and then feeding the gray shales. Below that, there's a channel that's migrating around, producing belts of channel sands in orange, encased in green alluvial facies, and so on and so forth. And the degree to which channels migrate, make wide bodies or narrow bodies, is controlled by things, okay? And there's two ways you can get at these dimensions. One is to just go out and field and measure them, right? But that's not that's only gets you so far, because you need to understand what controls those dimensions, right? And that comes back to what's the physics controls whether a river produces a sediment body that's 10 kilometers wide versus a kilometer wide, or whether it's amalgamated at a continuous unit or separated by, you know, a million little shale layers. And so to determine the dimensions of these geobodies, you know, we can do subsurface mapping. These days you can take 3D seismic volumes and look at the systems in 3D directly. I've primarily worked on outcrop analogs, a little bit of work on modular analogs. And then we get to this issue of scaling relationships. Tony Reynolds was a postdoc at McMaster when I was doing my PhD. He went on to BP and put together this diagram in which you've got width on the vertical axis and thickness of sediment bodies on the horizontal axis. The thickness is what you typically penetrate with a wellbore. So of course, subsurface geologists are always trying to say, if you have this thickness, what's the width? That's the big question, right? And the question is, do you use analogs, do you use fuzzy logic, or do you use physics to determine those things? Okay. Then, in order to sort of get this idea of scaling, many years ago, I was working with Bill Hawk on the National Science Foundation Margins program, most of which was driven by structural geology, but Chuck Mittrow and others decided to introduce this source to sink program. And the idea was to look at a modern system and characterize the sediment from the point at which it's made to its final resting place. And the two sites that they picked in source to sink was the Fly River in Papua New Guinea and the Waipoua River in New Zealand. And here's a diagram from my colleague Mike Bloom that shows that the size of the downstream submarine fan is greatly changed. You know, if you have rises and falls of sea level, you have a small system that's just excavating the local material, then the submarine fan is simply vacuumed out and deposited as a little blob of sediment. However, if you have a system the scale of the Mississippi, sea level rises and fall, but all that's doing is changing the position of the shoreline. The overall flow through the system is controlled by that vast area of the Rocky Mountains that's delivering sediment to these monstrous alluvial fans. So the sink volumes are very different. And in the petroleum business, you're trying to predict the volumes of sinks because they contain the reserves of hydrocarbons that people are interested in. The Statoil guys now, Equinor, sort of start just looking at scaling of just whatever you can measure. You know, slope versus length versus width of the river, of the shelf, of the submarine fan, and put together a variety of visual diagrams that show these small steep gradient systems in the front shown in gray. And those would be systems like, you know, small New Zealand, where you've got, you know, the Southern Alps and the sediment gets to the Pacific Ocean very quickly, versus on the back, a system like the Mississippi, where you're eroding the Rocky Mountains, and it's a long way from the Rockies from the continental divide to the Gulf of Mexico, where those sediments get sink, and a lot of sediment gets sequestered on the way. And the question is, can you measure an easily observable part of the system, the river, for example, and predict what volume of sediments in those submarine fans? So that's the oil companies interested in these scaling relationships. Okay, now we're going to move on to a little facies model deconstruction. So Doug Camp was a master's and PhD student at Mac before I got there, and he finished his PhD and was promptly asked by the AEPG to write the chapter on river facies models in APG Memoir 33 on sandstone deposition environments. And when I was an undergraduate, we learned that there's two main types of rivers, meandering and braided. And there is, the synthesis work of Peter Friend, who was a Cambridge sedimentologist. And he pointed out that meandering rivers make little ribbons of sand in buckets of mud, and braided rivers produce buckets of sand. So, of course, this is great. We have a ridiculously simple facies model that says if you know the plan form view of the river, you can predict everything about the three-dimensional extent of sands versus shales, which is reservoir versus seals, or aquifers versus aquatards, right? So this is great. One facies model can explain everything about the conductivity of subsurface reservoirs. Okay, and so that assumes that the plan view geometry of the river is the only thing you need to know. And so this idea was then, this is Bill Galloway's, nice synthesis from the 80s. And again, it shows exactly the same thing. We've got sandier models on the top, muddier on the right, and essentially they're connected to the plan form of the river. Okay, but then they thought, wait a minute, you can't observe meandering versus braiding in a core, but you can measure grain size. So he said, well, there's bed load dominated streams and there's suspended load dominated streams. There's Shum's original 1960s data. The bed load rivers carry 85% suspended load mud, and the suspended load rivers carry 95% suspended mud. Wait a minute, they're all suspended load. There really is no such thing as a bed load dominated river. It becomes a source to sink issue. Why is more mud sequestered in a fluvial system versus transferred through? It's not obviously related to the plan view of the river. What's it related to? So in the 90s, people began to think about these things. Yes.
I'm so sorry. I know too little about rivers, and I just want to clarify this so I can follow. When you're talking about the river, the type of river, and then the sediment, are we talking about the sediments of mud or anywhere below the river, or is it just in the fan?
So we're talking about the river, which typically contains sand, and then the floodplain, which is the muddy material that's deposited when the river's in flood. That's typically mud, right?
I see. So everywhere the water touches, that's part of the system.
Right. So what this is showing is the deposits of river systems, and that includes their channels, and then the floodplain deposits.
Yeah.
And so the proportion of channel belt versus floodplain preservation is a very tricky problem that we thought we knew was related to meandering or braided, and it's not. Okay. And this is, in fact, the next slide. So what this slide shows is every imaginable amalgamation or isolation of channel belts as a function of the rate at which the channel is migrating. So if it migrates a lot, it makes a wide channel belt. If it doesn't migrate much, it makes a narrow channel belt. Then the river switches position, okay? And if it switches position and the system is subsiding, then you get floodplain deposited when the river's over here. And then when it comes back, the new channel belt is separated from the old channel belt by floodplain. So then we end up with very isolated channel belts. This is bad if you're trying to pull oil or gas out of a fluvial channel belt and you need a gazillion wells to get it out. In contrast, if you have a system that's avulsing rapidly, migrating rapidly with no subsidence, and it all gets amalgamated, then you get your classic bucket of gravel or sand. That makes a superb reservoir. Now, what's interesting is they show that every imaginable combination of mud-dominated river deposits or sand or gravel-dominated river deposits is controlled by the avulsion frequency, the rate at which the river migrates, and the rate at which the floodplain subsides. Notice how the word braided and meandering don't appear anymore. They're gone, right? So clearly the old facies models that they're either irrelevant, unless we can say, Do braided rivers avulse more rapidly than meandering rivers? Guess what everybody and their dog is working on who's studying rivers these days? The controls on avulsion. That's now become the big issue, is what controls the sequestering of sediment in the floodplains. So it just sort of shows how we've made these evolutions in our understanding of facies models for rivers.
And you also think of it in terms of, in the one case, the system's getting out of the channel and you're accumulating muds in the floodplain because you're flooding the floodplain. Whereas in the other one, you're containing within the channel.
That's my next slide. So another way to look at systems is, are the systems collecting water? Are they degrading in a trunk valley? Or are they distributing on the floodplain and delta plain, right? So obviously, if you're collecting systems, you're not distributing. You're collecting sediment. Then you get into that trunk river. If that's incised, it's passing through. And then ultimately, you're distributing. So that gets us into where are you collecting sediment versus where are you depositing sediment? So that's precisely the question. And obviously, one of the big controls in the Himalaya system is gradient. As ultimately the system gets so flat that the system starts to get into its backwater limit, so the river's starting to lift up, then it's starting to get more of its sediment on the floodplain, and you start to get these muddy fluvial systems. Okay, so I'm definitely a rock guy. So here's a variety of outcrops. A little person for scale. That's right. I know there's people online here. I did promise to. There's my student for scale there. And so on the lower, we've got. You can see these laterally increasing channel belts with floodplain muds and coals. So that's a very mud-dominated alluvial system. There's Crispaiola standing next to the Green River, and there's a nice channel there with some lateral accretion deposits. And then here's a photograph from the Farron. What that shows is this white scour. Above that is a floodplain, and this is hard to see, but there's a laterally accreting point bar with a floodplain below it sitting in a larger incision. Okay, the larger incision's the valley. The valley's big and it contains a small river and its floodplain in the valley. So now we've got sequestration of mud in the valley, going back to Brad's question, right? And the question, where are these in the system? Are we in the tributary part, in the trunk part, or are we on that downstream end? And I would argue that the left is in the trunk, the lower one is on the distributive thing, and I don't know about the upper right one. Okay, so that's kind of like my opening statements. I'm not going to go into an example. So my very first job out of my postdoc was with Atlantic Richfield Company. The job was supposedly in Texas, and they immediately shipped me up to Alaska to work on their largest asset, which is the largest conventional oil field in North America, the Prudhoe Bay oil field. It was discovered in the late 60s. It went online in the 70s. And by the 90s, they were starting to get declining production. They were concerned about and they were going into water flooding, gas injection to keep the pressures up. It was a complicated and expensive reservoir engineering project. And they were willing to spend millions of dollars to figure out the geology. So Prudhoe Bay Field is on the north slope of Alaska, on the Arctic Alaska tectonic block. And that's going to become the tectonics of this situation is going to become very important as I continue this talk. So there's kind of a general paleogeographic reconstruction of the area. So as the Arctic Alaska block sits today, it looks like the rivers come from the northwest and flow towards the southeast. But of course, that block is rotated dramatically. So in fact, those rivers originally came from exactly the opposite direction. And the whole block's been rotated 180 degrees, right? Now we have big questions in terms of the size and scale of the sediments that contain the oil and gas in Prudhoe Bay Field. It's a fluvial and deltaic reservoir. We want to know how extensive the channel belts were, how extensive were the shales, would they hold the water up, would the gas go all over the place, would the water rush through the thief zones?
I'm so sorry for the interrupt there. What is the time scale for this rotation? How long did it take for Alaska to do this?
Oh, it's going to be tens of millions of years, probably, maybe more. Yeah. Well, I can tell you why, because it's a Permo-Triassic reservoir that's turned to 50 million years, probably got to its present place. I should know that. I'm guessing it would be in the Cenozoic. So you're looking at 100 million years or so for that rotation to occur. Yeah. So that's a little cross-section of the geology. The the saccharogenic group is the unit that contains the oil. So it's a combined structural unconformity trap. And here's a cross-section of the oil field. So everything that's in color represents the fluid-bearing zones. There's mudstone at the base, then it goes into sandy delta systems. I'm going to show you photographs of all these facies in a bit, and then into all these conglomerates. The original oil gas contact was shown by the red-orange contact. As they pulled the green oil out, the gas is expanded. In addition, they're pumping water into the downstream part of the reservoir to push the oil into the middle parts. So when I was working on it, we had these remaining oil reserves, both in the lower part, which was the deltaic part of the reservoir, as well as the fluvial rocks. Now, I told you that I'm a facies analyst, so let's look at some photographs of the depositional environment. So there's a core with a well log, and so at the bottom of the shales at the base contain integrated shales and sandstones. We see sharp-based units with beautiful, gently undulating, mounded cross stratification. We interpret these as wave to hummocky cross stratification. There's a light level of burrowing there, maybe BI of 1 or 2 on a scale of 0 to 6. And we interpret, you can see some nice little symmetrical wave ripples here. So this is a fairly low bar debate, lots of nice little graded beds here. So these represent little storm flood deposits. Storms are putting the rivers into a flood state, spewing their sand in the offshore shelf environment. It wanes, and then some little critters come in and live for a while. Sometimes things get a little bit more bar-debated. We can see maybe a little Conycnus or Racelia burrow here. Again, this is low-angle cross-stratified sand that represents storm wave deposits, and the bar-tubation is getting a little bit more. We see an overall muddier units into sandier, and then we see these sharp contacts that represent a little upward coarsening, little progradation of some sort of distal shoreline, and then we get a sharp contact that puts a deeper marine shale on the shallower marine sandstone, and that represents what we call in sequence stratigraphy a flooding surface. And those flooding surfaces you can typically trace around over large parts of the field, so they provide sort of the basis for the correlation, okay, of the layered units. Then we go up into more cycles of deposition. Here you can start to see some load cast. So here we had a sand was spewed out during a storm on sediment that probably had the consistency of soup, and the sand sank into the soupy sediments because they were so waterlogged, because the rate of deposition of sediment plus water was extremely high. We also notice a massive reduction in the degree of burrowing, representing the physical chemical stresses from fresh water and high sedimentation rates that basically decrease the ability of filter feeders and animals to enjoy the day. So we start to see the effects of the river in diminishing the biogenic footprint in the biotubation of the units. These coarsen up into flatline sandstones. The dark layers represent ripped up bits of plants that have been deposited during low flood stages, and we interpret these as upper shore face perhaps to beach deposits. Boom, we get a sharp contact with the shale above, another little flooding surface. And that flooding surface we can correlate to separate the porous sandstones below from the shales that can basically represent traps or seals for the fluids within. As we go upwards, we start to see erosive surfaces. You can see a little scour pit here, overlain by an obviously coarser sandstone. You can see some white so-called microporous chert with little bits of shale fragments here. And these now represent the basis of channels, probably distributed channels that are building out over the delta. So you see this overall upward transition from shelf facies to deltaic facies, and then into the channel facies. So these are the terminal distributory channels that build out over the delta. You can see it's coarser grained here. We see nice evidence of medium to very fine sandstones. These show ripple cross lamination that's unidirectional, indicating unidirectional flows, hence waning channel flows. And then there was another flood, and we see a coarse-grained sandstone top that represents a renewed river flood that put a coarse and medium sand over the very fine lower rippled sandstone below. So we can start to see these flood cycles in the river deposits. As we continue to coarsen upwards, we start to get these spectacular conglomerates, okay, getting up to 2 to 3 centimeter pebbles, okay, and these are pretty coarse-grained for river deposits. And the question is, we'll get into the question of what these channels are in a bit. Just want to do these observational phases. Here we see some nice, rather moderately to poorly sorted, but well-rounded class supported fluvial conglomerates. Sometimes we see good evidence of dune scale cross stratification, representing the migration of underwater dunes through these energetic flows. And then you can see a set boundary there, and you can see that the grains are getting quite poorly sorted, which is diagnostic of the high shear stresses of fluvial gravel bed rivers. Then we get into mudstones that start to look very different than what we saw before. I think you can all see that they're dominated by these vertical cracks. These are indeed desiccation cracks. And we get roots and plant material. And so now we're starting to get into the floodplain shales that are very different from the marine pro-delta and shelf shales below. So we see completely different types of shales as we get up into the stratigraphy. And one of the big questions is, what's the extent of these non-marine floodplain shales? They have these classic red bed color. You see slicken sides on the surfaces that are formed by the wetting and drying of these muds as they're exposed to the air. So that's kind of the end of the observations. Then the question is, okay, great. Now we've got a basic idea of the deposition environments. How do these sandstones and conglomerate correlate? More importantly, how big are the channels? Are these small rivers, big rivers, continental scale rivers? Does it matter? If the rivers are bigger, how are they behaving? The bigger the river, presumably the wider the channel belt. And perhaps, and what controls the amalgamation? Where are we in the system? Are we kind of in the trunk systems with lots of sand downstream, or are we at the end of the system? I try to convince you that we see the entire transition from delta to terminal distributary channel to conglomeratic trunk channel. So we think vertically, we see the whole source to sink system. And then, of course, we see these gravels. What controls the gravel sand transition? As you can imagine, anytime you're interested in fluids and porous media, the porosity and permeability is controlled by the grain size and the sorting. So the companies were very interested in that conglomerate because that's a key target. And so the question is, can this analogs and source to sink scaling help? Okay, I'm going to take a breath here. You guys to digest. So anyway, so I get up there with my buddy Bowtie, Robert Spence Tie. His nickname was Bowtie. And and I just finished my PhD correlating cladoforms in the Dunvegan Delta in Alberta. And I get up to Peruta Base, like, great, another fluvial deltaic system. I'm like, oh my God, what is this pinch and swell stratigraphy? Like, there's the shales in gray, then this kind of salmon color is the sort of delta front facies, but they've got the whole thing correlated as kind of like some sort of pinch and swell laterally continuous thing. And then the BP engineers were telling the geologists, pick this little shale here, that's the 14N shale, pick it in every well. I'm like, it probably doesn't exist in every well, it should cladoform. So we went ahead and redid the correlations. So that's sort of the before picture, which was the state of the art for the largest conventional oil field in North America in 1991. And Pete Barker, the manager, said, yeah, my geologists haven't gone on a field trip in 10 years. I'm like, yes, no wonder you need someone that's just got a little bit more recent experience. And you see the difference? It's a lot of different things. You see the sandstones way down at the bottom. Well, we predict that they connect up to oil-bearing sandstones higher up, which means that's potentially bypassed oil. Boy, you go to Exxon or Shell and say, we've got 5% of additional recovery in a 24 billion barrel field. That's hundreds of millions of dollars of additional value to the company, right? So a lot of interest in these new ways of thinking. Plus, our shales dip, which means the very way that we think that the flow units and flow barriers organize is different than the layer cake strategy used by the engineers and the geologists working before us. This now is a correlation that Bo did of the entire reservoir. So the work that he and I did together is the lower part, and then Bo continued his work and worked on the fluvial stuff, which is these purple floodplain deposits and the orange conglomeratic fluvial deposits. And big questions about how extensive these purple units are, because once you've got these purple units, flow can't get across it. So you need either horizontal wells or other technologies to get the oil and gas out. Now, the other thing you'll notice, I've circled areas where we have evidence of a single sharp-based firing upward unit. So we said, can we find evidence of a single channel fill? Not multi-story, but a single channel fill that gives us a window into the depth of the formative rivers. Okay. And so here's a close-up look at that. So you can see some nice isolated finding upward channel fills in pink here. So the thickest channel fills are about 12 meters, 40 feet. Those probably represent what we call the tailweg scours, so the deepest part of the river. The mean backfill depth is probably about half that. So we think on average, the rivers were mean backfill depth is maybe about 6 meters, okay? So now we have our first paleohydraulic parameter. And there's another more detailed description of these fluvial systems that shows the distinction between the bar deposits that occur within the channel versus the stories, which represent the fill of one channel depth, okay? And again, you can see there's good evidence of multi-story fills. The channels are building up through time, and we think the stories get up to, as we said, about 12 meters deep. Now, this diagram comes from John Bridges' textbook. John is a famed fluvial sedimentologist that some of you may have certainly at least heard of. It shows shear stress on the vertical axis, grain size on the horizontal axis. The lower red line represents the Joulstrom diagram. That's the threshold of movement. So given a certain critical shear stress, the grains begin to move. The upper diagram represents the point that grain will go into suspension. And the area between the upper red line and the lower red line is the bed load envelope, right? So what it shows is that high shear stresses, a wide range of material is moving this bed load, poor sorting. At lower shear stresses, a narrower range of grain sizes moves in bed load, better sort, right? So the poorer the sorting, the higher the shear stress. Now, in addition, you can look at the nominal diameter of the grains from the core and then figure out what the shear stress is. So now we've got water depth, we can get the shear stress. We're starting to put together the paleohydraulics of the system. So it looks like we need about 12 to 20 pascals to move those 2 to 3 centimeter grains. Now, I'm very interested in the slope of the system because that starts to get to questions of tectonics. If you've got a slope, that tells you how high the elevation was at its maximum. So we figured that these rivers were flowing over slope, so there's the standard diagram for shear stress. It's the density of the fluid times the gravitational constant times the depth times the slope. We have depth, that's the 6 meters. We've got the gravitational constant, we know the density of the sand and of the water, so we can rearrange that, and we know the shear stress, we just calculated that. So we can rearrange that and calculate the slope. We get a slope of something on the scale of 2 to 3 times 10 to the minus 4, or 0.01 to 0.02 degrees. Okay. And we can also just look at tables. So there's very coarse to coarse gravel, and we can use that to calculate the boundary shear velocity, the critical shear stress. And so it looks like these rivers were moving at a velocity of about 0.12 to 0.14 meters per second. Sorry, the critical velocity. Now, the average velocity is going to be about 10 times that. So basically, the rivers are moving about 1 meter per second, and most rivers flow at about 1 meter per second. Turbidity currents move about 10 times that velocity. So there's the old Shazy equation, and we could rearrange that to estimate the average velocity. Okay. So now we've got something we don't know. What's the width? We've got the depth of channel, we've got the velocity. What's the discharge? Well, for that, you need to know the width. And so for that, we just use empirical equations. Okay. There's lots of those floating around. So we're going to assume an area that ranges between 4 to 2,000 square meters. And we get a possible water discharge on the scale of 500, 2,600 cubic meters per second. Now, the next thing we can do is there are equations that say if you know the depth or you know the discharge, you can get a feel for the area that's being drained. Now, this is something we want because this gets us to the paleogeographic and plate tectonic reconstruction, right? What was being drained to produce the water that was flowing in these rivers? And so here's an example of these empirical relationships. We've got a couple of modifiers. We've got the area, and D would be the channel depth. And there's an equation that also solved that for Q. And so if we take this equation and solve for A, we get an area on the scale of about 100,000 square kilometers. Okay. Now there's uncertainty here. These aren't great numbers. They're probably okay to within an order of magnitude. So, the big question we had is, what was the size of the river feeding Prudhoe Bay, and where was the sediment coming from? Thank goodness we have other scientists. This is Miller's work from Stanford. So she did some detrital zircon work, and of course the detrital zircons, you take them out of the sandstones and you measure the ages of the different zircons, and if you've got Archean zircons, that tells you you're draining Archean terrain. If it's Paleozoic, it means you're probably eroding a Paleozoic fold and thrust belt, et cetera, et cetera, et cetera. So she collected detrital zircon from the Evershack sandstone in the outcrop. I'd like to do that for these cores, and found predominantly Paleozoic zircons. No evidence of anything coming from the Canadian Shield. Okay. So this is basically her work. So here's the Arctic Alaska block. Okay. We've got this Trans-Laurentian River that was a continental scale source to sink system, draining the Canadian Shield. So that should have a very distinctive detrital zircon signature. Okay. So she did work on the Paleo-Arctic systems from the Urals, Russia, all the way into North America, and mapped this Trans-Laurentian drainage. And I sort of thought, oh, maybe that's what's feeding the Prudhoe Bay field. So I did a very simple, kind of goofy Janok Bhattacharya experiment. I just drew a stupid oval that was about 100,000 square kilometers in area and stuck it on the Miller map. And it's clear that there's no way that the drainage area that we calculate for the Prudhoe Bay is big enough to have accessed the Trans-Laurentian drainage system. And what's great is that the DZs proved that it couldn't have accessed that system. It doesn't have the lithology you would expect if it was draining the Canadian Shield. So it's kind of a nice example where we can use sort of a bit of these physical scaling relationships to figure out where the system is coming from. Now, my good buddy Ashton Embry, who spent his life at the Canadian Geological Survey, hypothesized this thing called Crocker Land that fed sediments into the Sverdrup Basin where he worked. Now, it's clear even from my reconstructions that the Prudhoe Bay drainage area is too small to have accessed Crocker Land directly, but it probably represents sediments recycled from the Sverdrup Basin. Okay, so we can start to get a feeling for the paleotectonic land masses that were delivering sediment into this supergiant oil field. Okay, that's the Prudhoe Bay story. I've got a few minutes left, so I just want to. The other big thing we did in ARCO was look for outcrop analogs to Prudhoe Bay. So in addition to this work I've done recently, which is new work, using the source to sink concept and scaling relationships, before we got there, we said, are there any ancient analogs to Prudhoe Bay? And we went to see the Farron Sandstone in Utah. So that got me working on Farron. So there's a paleogeographic reconstruction of the North America during the Turonian time of ultra greenhouse with a series of small source to sink systems draining the Paleo Rocky Mountains that were feeding into the western margin of the Seaway. And I've worked on most of these systems over my career. I love the deserts of Utah because the outcrops are continuously exposed. The mudstones are exposed. There's bentonites at the base that you get for datum. And so, the only thing is you've got to measure lots of sections to capture all the geology, but it's sort of all laid out for you. And, and you got to be able to get up those vertical cliffs for which we began to use ropes, which is a whole nother story. So I had a PhD student, worked on the Farron, and here in this nice hogsback, you can see all the different, these upward coarsening delta cycles we call parasequences bounded by these flooding surfaces. And this is an example of the stratigraphy that he walked out in these beautifully and continuously exposed outcrops. This is the cross-section he put together. And I was talking to Brad last night. Brad was explaining to me that the cross-section belies the incredible amount of detail a number of students it takes to put together the stratigraphy. The pink dots in the bottom represent the measured sections. The dark blue represents shelf mudstone. The pink layers are these ash flow tuffs or bentonites. And sometimes they're exposed. Sometimes you've got to trench with a pickaxe to get it. But without that, without these isochronous volcanic ash layers, there's nothing to hang the overlying stratigraphy. So one of the advances we made was just said, we want to get the story out of these outcrops. We have to have a good isochronous datum. Because, what's exposed is the cliff geology. Look how complicated it is. Sandstones come and go, they dip, they're not continuous, and the only way you can get this kind of detailed reconstructions is to measure lots of sections and then walk out the contacts in between. I'll go back to that beautiful example of an incised valley with a floodplain on top of it. And I think you can see the accreting point bar deposits in the sandstone above. So that allowed us to distinguish the valley, which is the larger trunk system, and ultimately filled by a smaller river at some later date. So that river may not even have cut that valley, right? That might have been a later transgressive valley fill. The fluvial sediments show poorly sorted conglomerates with centimeter scale pebbles similar to what we see in Prudhoe Bay. These pass up into mud-dominated fluvial systems. You can see a nice channel margin next to the geologist. Beautiful example of an in situ tree. That's a little floodplain lake. That was the top of the lake, and the rest of the tree is oxidized away. And here we can see a nice muddy meander belt in which there's later reoccupation by a coarser grain channel. You notice how the meander belt is moving over a coal layer, because the coal is very difficult to erode. So once you get coal there, the rivers can't cut the coal. So if it hits a peat, it tends to move laterally and deposit another river. And then when a new avulsion takes place, the channel says, oh, I'd rather go where the old channel was, because that's easy to erode. The peats are they're like rubber, okay? Now, once again, we've mapped these systems in 3D. So there's our paleogeographic map of one of these parasequences and the river that feeds it in the Farron. And we said, wait a minute, let's look at the trunk river. That's the largest river in the system. And we can calculate, we can measure the depth because we can see it. We can actually get the width of these channels. They're actually exposed in plan view. There it is right there. There's a beautiful plan view exposure of these meander belts. So we can get the meander belt width, the curvature, the wavelength, as well as channel width. And we can use all that using similar criteria I showed you in Prudhoe Bay. We've got the channel thicknesses. There's the bed form phase diagram. It's another way to get the velocity. And we figured that these channels are about 4 to 5 meters deep, bankable depth, with discharges on the scale of about 402,000 cubic meters per second. Well, that's pretty close to Prudhoe Bay, isn't it? Right? And the work on Prudhoe Bay really pushed me to start thinking about what scale of an ancient system is actually appropriate. I didn't know the Farron was until decades later when I finally did all this math and said, yeah, at least to an order of magnitude, they seem to match pretty well. So why was this important? So we had a hypothesis we were testing in the Farron. There are several big delta wedges, and one hypothesis is there's a big river that avulsed every once in a while. The other hypothesis is that there were separate rivers with separate drainages. Right? So those are very different hypotheses. Is there a single trunk river that's fishtailing around, like the Po, or there are multiple drainages? I'll skip through this pretty quickly. Once again, we thought, let's try detrital zircon analysis. In the Western Interior Seaway, you've got two major sources of detrital zircons, the fold and thrust belt and the Cordian magmatic belt, and then this much older Mogollon highlands. So you get this very old signal show from Mogollon, which is an uplifted basement block, and then you get these much younger zircons from the fold and thrust belt. Turns out in the Farron, we see two completely different source areas. So it turns out that the Farron Delta is actually fed by two separate rivers that feed separate deltas that kind of interact with each other. So it's a pretty disaggregated source to sink system. What's interesting, we went back and did some very old work called petrography, and we just did simple point counts, and we demonstrated that, forget the zircons, that the composition of the sandstones is completely different, right? So the zircons demonstrate different age source areas, and then we demonstrated with a much cheaper measure called cutting a thin section, we could distinguish these two different source areas. And in fact, if you start to go back onto the rocks carefully, you see a slightly different color in the sandstones because they're compositionally different. Okay. Now it's a very complicated story, which I'll go into, but blue represents the severe drainages, and then the pink represents the Mogollon things. And they're all kind of mixed together. So it's a very complicated system. The guy that got me thinking about this was Mike Bloom, saying, well, look at all these quaternary valley systems. They look very different than what your students mapped. And so we basically forced our maps to look more like the quaternary, using guidance from the modern patterns to interpret an ancient systems. And that allowed us to test the hypothesis. Okay. Now, the big question we had in Prudhoe Bay was, how do you correlate? So here we've got 3 cross sections of Farron wells that we drilled in Arco days with 3 different correlation schemes. The bottom shows valley fills. The upper 2 assume there's no valley fills. The details don't matter. So I've done a lot of work on the Farron, and there's an interesting story here that people haven't cottoned on to. So this has now become a part of the new SEPM sequence stratigraphy graduate workbook. So this is the data set that one of my students put together, and I've given this to probably hundreds and hundreds of students to correlate. It's hung on a bentonite datum at the base. Yellow and gray is marine shales and shorelines, and red and purple is floodplain. I'm like, go ahead and correlate. Now, of course, the advantage is we've walked all this out. But without walking it out, what would you do, right? So there's sort of, quote, the answer, right? So an answer, right? So there's just the key surfaces. Then we can add in the facies, right? You know, that student probably got a 80 or 90% on that answer. So I went ahead and decided I'm just going to compile the different correlations by different students. And I do these things, then I put them on the wall, and I say, okay, this student's liberal. They're smearing it all over the place. This student's very exacting conservative. They're disallowing the channels to expand, and they have Christmas trees. And I say, I say, what does this tell you about your personalities and your willingness to go beyond the data, right? We don't talk about bias in our geological interpretations enough, right? Because we all make interpretations of geology, and all these students got A's, and yet they have quite different looking correlations. And some of them look pretty funky. My favorite one was this one. This student used a very old technique of just recognizing vertical exaggeration. Look, even though that looks like it's dipping at 45 degrees, it's really only at 1 degree, right? And then, of course, it goes back, well, what was the dip in the Farron? And of course, we can compare a student example to the actual example, right? Then we go back to our Prudhoe example. We go like, well, did we get it right? I assure you, you always overcorrelate. If a manager or oil company says, here's some wells, correlate them, what are you going to say? I'm not going to correlate those. What do you think I am, crazy? Of course you're going to correlate them, you're going to get fired. But then if you overcorrelate, then you're overestimating the continuity of that reservoir, and your company's going to be too enthusiastic, and they're going to lose money, right? So now this is just a little, Brad's still here. So the other thing we can do with this data, I skipped through this, we can look at the trajectory of the stacking of these shorelines through time, right? You notice that 10 is very close to the bentonites, the other ones are further away. We can use that to do a shoreline trajectory analysis that measures the rate of aggradation and progradation and the magnitudes. We can stick that into Wheeler space. I couldn't give a talk in this lost room without a Wheeler diagram, tempered with radiometric dates that we've done. Then we backstripped all that, took out the tectonic and compactional subsidence, generated some sea level curves. The red is the composite curve, the blue is the leftover curve, and then ultimately put together a composite sea level curve for the Cretaceous on the left, that Brad and I are going to talk about this afternoon, and then compared that to the global cycle chart to see whether or not the high frequency cycles in the Cretaceous interior seaway seem to correlate with global cycles. And the short answer is, it looks like they do. This work hasn't been published, but is soon to be. And we've got 10 minutes left, so thank you for listening. Sorry for the rush job, and be happy to answer questions if you haven't.
I'll ask you questions later because I gotta go teach.
Absolutely. Yes.
Hey, my name's Luca. Thanks for having me do that talk. Actually, during my first graduate seminar when I was still an undergrad, I had to give a presentation on one of your papers, and I remember it because the title was Deltas, which I've always felt was like mic drop, like good swing. Like, what do you mean? You don't believe me? The title's Deltas. I know that. I know what I'm about. And my master's work had me delve into a lot on the Amazon river system, and I've always kind of wondered, how does the Amazon, so largest river system in the world, about a third of a spear drop, so 300,000 cubic meters per second is the estimated discharge of the Amazon, largest by far in the world. How does that stack up to paleo river systems? Like, is the Amazon still the big kid on the block, even when we look back through time? Or
Well,
are there some river systems that approach or exceed the?
I don't think anyone's ever found a river any bigger than the Amazon.
Okay,
And it's interesting because when would you expect the bigger rivers on planet Earth?
yeah, I mean.
Well,
Flatter?
no, during Pangea, right? When you had a
Right.
supercontinent, right?
Right.
That's the only time when theoretically you have a larger landmass, right?
Right,
The question then becomes where the drainage divides, right? So we know that the Paleo Appalachians, Caledonians would have been a major drainage divide.
right,
There was a paper. So in fact, one of the reasons why Liz Miller is doing the Triassic work is the Triassic is considered at the time Permo-Triassic of the world's biggest rivers. So again, that was our interest in Prudhoe Bay. We want to, well, could it have been a river that was big in the Amazon? In fact, interestingly, it isn't,
right,
right?
right, that's,
Yeah. Now, there's a recent paper that I reviewed on paleo delta systems in the Arctic, written by a Norwegian group. And they claim to have the largest delta plain ever in the world. Again, that reflects a Pangean scale system. But whether or not it was fed by one river, like the Trans-Hudson River, the Trans-Laurentian River that Miller mapped, I don't remember. But people are onto this paleo drainage, and the place to look is Pangea. So you look at you look at the sink systems in the Pangea, and then you go back to their rivers and you see if you can find something bigger. I don't know of any river that's ever been discovered. Now, the other big river in the Cretaceous, which is a separate talk, is the McMurray. And that's a continental scale river that gets up to 30 meters. Again, well documented by integrating detrital zircons and mapping. So there are continental scale rivers through time. My guess is that, obviously the physiology of the continent, the climate patterns, they all go into determining the size and scale of the river. But Pangea is your best bet to finding rivers bigger than the Amazon or Mississippi or the world's big rivers today. And also, climate plays a role because the more precipitation, the more water, the more discharge. Yeah.
right, the Amazon benefits from being so close to the ITCC.
Right, exactly right, yeah.
Whereas Pangea might have been largely drier, right, as we move.
Depends, when you get, didn't really start to get humid until kind of Jurassic, it was breaking up, yeah. Mhm. Yes.
So thanks again. This was very much appreciated, the connection with how rivers work and then how maybe the solid part of the planet works, like plated planets. So to me, you're pondering mostly because I know very little about anything rivers. I'm trying to set a context for the time scales. Right, so you mentioned I got some velocities from you, meters per second, over which these rivers flow.
Correct, yeah.
You have this very long time scale of tectonic plate motions, and the equation that stuck out were your shear stresses and the relationship to slopes. So there's this centimeter per year time scale over which you have lateral motions, of the plates moving,
right,
potentially changing the slopes. There's some time scale, which I don't know what is, of, mountain building or any kind of topography changes. That again could be centimeters per year, could be faster maybe. So
centimeters per year is pretty fast. Millimeters per year is a pretty good sort of subsidence rate for, the average foreland basin. In meters per 1,000 years, or
if you cut it in, right?
Or uplifting, yeah.
Okay.
Yeah.
So there's that time scale as well. So when you're making this evaluation, I guess I'm trying to understand the lifetime of a river.
Yeah,
And
so
the slope changes when you're providing these numbers, which is a single number.
correct, yeah. So I skipped a lot, obviously, because to get sort of a story told. To do the source to sink analysis, we start with this instantaneous discharge. Then the question is, okay, so the river's flowing at 1 meter per second. Great, it's got a discharge of 2,000 cubic meters per second. But it's not flowing 24/7, 365 days a year, right? So then you can go to the hydrograph literature, and on average, most rivers are flowing a week to 2 weeks a year. And then the recurrence frequency for rivers, which is the flood frequency, depending, very climate driven, it could be once every 5 years if you're the Niels River in Australia, or it could be every year if you're the Ganges in the monsoon. Okay, so then we can look at the coals and paleosols in our ancient systems. In the case of the Ferren in particular, the palynology shows it was ever wet. right? So we assume that the rivers were in flood about 2 weeks a year, and the rivers probably flooded at least once a year, okay? Then you've got the actual chronometric data, which is getting down to Brad Singer claims 0.02%, but the dates he gave for us weren't quite that good. So for a 90 million year old rock, we were getting plus and minuses of down to about 100,000 years. Okay. So, you know, and you've got a couple of days. So, you know, the entire ferrum I talked about is deposited within around 500,000 years, plus or minus. Okay. The whole thing. Right. So that's getting towards the limit at which you begin to expect, you might expect to see some tectonic change over 500,000 years, but not a lot, right? And when you're in the Milankovitch frequency band, which is tends to 20, 100,000 years, probably not much, right? So you can sort of ignore tectonics at a certain scale, but then you need to start to worry about it as you get to longer time scales, right? The other thing I tell people is, you know, one of the arguments, in fact, Sloss used to go on about this. He gave a talk on a countervailing view, because he was very concerned that his student Pete Vail was so focused on used to see that he was ignoring the tectonic control on cycles. This is a complicated story because Exxon are a big company that have no interest in telling you how they do their business. And I work for them, and they love plate tectonics. But the fact that they loved it was their business. So they said, look, we understand the tectonic control systems, but what we don't know is where the sediment is from the shoreline. So let's focus on solving that problem because tectonics is solved. So when they published all of their sea level cycles, they neglected to mention that they understood the tectonics well. Okay. And so people like Henry Postman would say, well, tectonics usually doesn't matter. Well, it actually does matter. And I went, wait a minute, this is just simple. Tectonics requires lithospheric deformation. When you rise and fall sea level over a few thousand years, it doesn't deform the lithosphere very much. Yeah, there's a bit of a hydro isostatic effect, but it's not huge. So I said, look, the way we identify tectonic sequence boundaries, they produce these things called angular unconformities. And when you drop sea level, you presume a disconformity with no evidence of lithospheric deformation that tilts the rocks, right? And we've done a lot of work in the Cretaceous interior seaway. Now, that the part of the problem is if you have a cloniforming unit that dips at 1/4 degree, and then a unit erodes it looks like an angular unconformity, but eventually those cloniforms flatten out, right? So it's not, right? So if you can distinguish true angular unconformities from disconformities, you can start to distinguish static controls from tectonic controls. And also in another project I didn't talk about, you see big slopes. So in the Blackhawk Castlegate, the Blackhawk rivers go west to east. The Castlegate rivers show a 90% change in orientation. So the paleoslope changes. If the paleoslope changes, the lithosphere is deformed. Excuse me, right? So you can look for slope changes in direction of sediments. Most of those things probably indicate the tectonic controls. And then if you've got good age data, you start to get the timescales. And do you know much about DZs? No. So if a detrital zircon represents a zircon grain that's in a sand or sandstone, okay?
Oh, I'm sorry, I do know zircons, I just wasn't familiar with that.
Yeah. So in the Cretaceous, you've got volcanoes blowing up, and so they'll deposit zircons when the river's flowing. So the very youngest zircons in an ancient river deposit can be close to the age of the river, right? So you can start to get the age of river sediments just by looking at the age of the zircons contained within, right? The problem is it's detrital, so there's a lot of mixing. It's not as accurate as a volcanic ash layer, and you need great precision. And the problem is, I kind of work in Milankovitch frequency, 20 to 400,000 years, and even in rocks 100 years old. This is why I'm here to visit Brad, because he's doing astrochronology. He thinks he can get Cretaceous systems down to the closest tens of thousands of year cycles, right? And that starts to allow you to distinguish geomorphological controls that are eustatic versus tectonogeomorphological controls, which I think is what you're asking about, right? Yeah. Yeah.
What about in Asia before the Himalayas, the Indian subcontinent collided with Asia? Was any research on river flows there?
Well, so I'm writing a textbook on Earth history textbook with my buddy Pete Copeland, and he's an expert on the Himalayas. He does a lot of thermochronology. So what that is, you get something like an apatite, right? And that gets reset at a very low temperature, whatever it is. Someone knows better than me. Let's say it's 100 degrees Celsius, right? And then you find that apatite crystal in a river deposit, and you say, oh, it's 10 million years old. So 10 million years ago, that apatite crystal was buried 2 kilometers below the surface of the earth, and it's ended up in a river X million years later, right? So you can use thermochronology for minerals that are set at relatively low burial temperatures to figure out, when they were in a mountain versus when they're in a river, right? The other person I know is working on Himalayan rivers. Two of them are Peter Clift and my colleague Livio Giosan at Woods Hole, and they're looking at the Indus, and they're looking at avulsions in the Indus, and civilizations live around rivers, right? The river switches. Your city's not so valuable anymore, right? So they're looking at switching of those rivers over kind of tens of thousands of years of timescales.
Thank you.
Sorry, can I cut in real bit? Because Himalaya is rising relatively fast.
It's fast, yes.
So your slope is also changing
Right.
relatively fast.
Yeah.
But how fast, do you know?
I don't know, no, yeah. I think that I remember reading this when I grabbed. I think was it Terry Jordan's? I forget now. Taiwan 4 deep is going down at 10 meters, 10 meters per 1,000 years. It's probably one of the fastest falling basins in the world. So there are kind of, and of course, and it's not that hard. I mean, we know from glaciostatic rebound how fast the lithosphere moves, right? And as soon as you start eroding, the basin starts to lift up, right? So you get this feedback effect, and there's lots of people that model that stuff, the Chris Paolas and Lake Paul Hellers and other people, Chris Beaumont, they're the leaders in geodynamic modeling, which is not my field at all, but it's again, it requires some physics, understanding of rheology and timescales to kind of get at these problems. Yeah.
Great, well, thank you. If there's no more questions, we'll adjourn.
Thank you for the questions too.